Okay, homework 8, page 144, section 3.3. 1 through 19 odd, 43, 45, 57, 61, and 71. This is 15 problems, and that's about what it's going to be from now on. 15 to 20 problems, pretty much for every homework, maybe more. So, get ready for that. Now, here we go. Let's suppose that f of x is a constant. Okay, so c is a constant, and it will be throughout the whole lecture, and probably throughout the whole year. What is f prime of x?
It's f of x plus.
Yeah. Okay. Well, let's do. Okay. It's the limit, right?
Yeah, the limit.
By definition, it's the limit as h drops to 0 of f of x plus h minus f of x all over h. Now notice, it's not f of x plus h. Right? It's not the outputs it's the inputs that we're adding h to, because, yeah. But if f of x is just a constant, you could say, what's its slope?
0.
The slope is just 0, right? And so this limit should be 0. And indeed, let's just do that. Plug in, you go to your favorite x, and then you go to your favorite x plus h. You plug it in, and you get out a 0. Well, plugging it in, yeah. When I plug it in, I get a c. And then I subtract off, I go back to x and plug it in, and I get, again, a c. And so this is just the limit, as h drops to 0 of, well, that's just 0 over h, which is just 0. And I had this whole long spiel I was going to give about this today, because you might not be convinced by that. I know I'm not, because on one hand, we have we've had limits where, and indeed, every limit, if the denominator is going to 0, well, the top has to also go to 0, otherwise it blows up, right? And so it's like, well, how do we know that this doesn't go to something else? I mean, if you get 0 over 0, isn't that 1? Or whatever, or it might be something else. I had this whole long spiel worked out to really drive this point home that this works. But we'll get into that later this year, actually, and so I'm just going to leave it at that. Do you buy this?
Yeah.
Right, it does make sense. It's like that's already at 0. H, you never actually plug in 0 for h, do you? Right? That's the whole idea of a limit, right? Because if you think about the definition of the limit, right? Like as x goes to a, that means that the distance from x to a is like less than delta, but it's also bigger than 0. So you're never actually plugging in the value. So h, you don't actually plug in 0. And so if h is any number besides 0, well, that is 0 then, right? 0 divided by 1/100 millionth, still 0, right? So I had this whole long spiel, but when we do something later this year, we'll get into that, right? But I hope that's convincing enough, okay? Do we all buy this? And also the geometric interpretation, right? You have a constant function. That's just a straight horizontal line. What's the slope of a horizontal line?
0.
0. And so the slope of that function is 0 everywhere. And so the derivative of it will be 0. Okay? Okay, so we all buy that. And one way we could write this is dx. You take the derivative of what? Well, of a constant. And what you get is 0. What we're going to do today, the same way that we did with our limit laws, right? When we first did a limit, we plugged in a bunch of values and did a bunch of stuff. Now when we first discussed and then with the limits, what we did is we figured out limit laws to make the process of calculating limits much easier, right? And we got to a point where it was like, well, you could just plug it in, right? And that's what we ended up doing. Now we're going to do the same thing with derivatives. What you've been doing is using this clunky definition that the f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. And you have to go through and calculate that and take the limit and blah, 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 blah. But now we're going to get past that, because we're going to come up with a bunch of, now instead of limit laws, they're derivative laws. They're laws about derivatives that will make our our lives easier, where we could calculate a derivative without having to resort to this clunky definition right here. The definition's still true. We're going to be using this to derive everything. But once we have those laws in place, and as you will see very shortly, taking derivatives will become much easier on us. So that's our goal for today. And on Thursday, we're going to figure out a bunch of laws for derivatives. Everybody with me on that?
Yes.
The first one right here is this, okay? That the derivative of a constant is 0. Does everybody buy that? Okay, now here we go. Here's our second one we want to work out on. If your function is x, then the derivative is 1. A couple ways of seeing that, right? This function is a line, and it has a slope of 1 everywhere. Another way, we could take the limit, right? And I'm going to really blow through this. F of x plus h minus f of x all over h is the same thing as the limit. X plus, oh, that's easy. That's just x plus h minus f of x is just x all over h. Those guys cancel. We have the limit of h over h, which is just 1. The limit of 1. The limit of a constant is the constant. You're going to start to notice that a lot of these things that we're deriving here are going to be, they're going to follow very closely, but not exactly with the limit laws. Today, I think that they will. But we could do this with prime notation, or we could say that the derivative of what? The function x is equal to 1. Everybody buy that?
Yeah.
No questions there? Nobody want to? Okay? So, again, this is nothing new. We've done all of this already in class, but now we're formalizing all of this. We want to have this in our toolbox, right? It's the same way we had limit laws, and we had to figure out, well, the limit of a constant is a constant. We need to figure out the derivative of a constant is 0. The derivative of like we also said, the limit as x goes to some a of the function x is just a. Now this is kind of the same thing going on here, right? It's a little different, of course. So now we're not just plugging numbers in, we're actually taking a derivative. But we want to build all this up, okay? Everybody with me so far?
Yeah.
Okay, now, here we go. Here we go. Now, in class, like just now, and before, and in homework 6, this might not be fresh in your mind because that was like 5 days ago, but we found the following things. So first off, we'll put this one right back up on the board. If f of x is x, then f prime of x is, what did we just say? 1. 1. Okay. Now, we found this one before. I think you did this both in class and in the homework. If that's f, then the derivative of it, does anybody remember this?
2x.
2x. Okay, yes, that is true. We could go through and do the whole limit and blah, 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 but we've already done that. In your homework, you did this one. And I saw that both of you did it correctly. So when I say you did it, I tell you did do it. If the derivative was this, now do you remember what it was? You don't have to remember. I mean, it's kind of hard to remember because, I mean, this is days ago and, like I said, 5 days ago. But it's this. And both of you guys got this correct, so I'm just copying right off of your homework. This is what you told me in your homework. You plug that into the thing. You had to factor out all the stuff, right? And you did that and you canceled an h. Then you could let h go to 0. The only thing that remained was this guy right there. And that, if everybody remembers, comes from the fact that when we go x plus h and we raise it to the 3rd power, we get an x cubed plus 3x squared h plus 3x h squared plus h cubed. Everybody familiar with that, right? Yeah. That's what you did. You subtract off the cubed. That guy goes away. There's an h here, so you cancel out all the h's. And the only one that doesn't have an h is this guy, and so when h goes to 0, that guy goes to 0, that guy goes to 0. He's the only one that remains. And you end up getting that right there. Okay. Now, one more that you also did. I think this was the last one from homework 6. If f of x is x to the 4th, anybody remember off the top of their heads what that one is?
4x to the 3rd.
4x to the 3rd. Are you noticing a pattern here?
5x to the 4th.
It looks like the next one's going to be 5x to the 4th. And pay attention here, because this is how you'll want to think about this. It looks like when you have a polynomial, or this thing, an x raised to a constant power, when you take the derivative of it, it looks like the power jumps down, and then you decrease this power by 1. Let's just see, right? Right? So like when x is to the 1 jumps down, and you decrease this power by 1. Oh yeah, it actually works there too. The power jumps down, and then you decrease that number by 1. The power jumps down, and you decrease that number by 1. The power jumps down, and you decrease that number by 1. So I'm guessing it looks like, so if that trend continues, what do you think if we had some number n? If we don't know yet, but if this pattern continues, then the derivative would be what?
X
n
to the n minus 1.
To the n minus 1. It looks like that's what it should be. Let's prove it. Okay, so here we go. That's my claim. All right, and so in other words, I'm claiming that if f of x is equal to x to the n, then its derivative is nx to the n minus 1. Now, you know, we probably could with induction, but we won't need to because we know the binomial theorem. We did this last year, right? We also did it over the summer. And so, let's just see, if I've given an f of x, and this is what I want to prove. So I'm just going to take f and just plug it in to the definition. F prime of x is equal to the limit as h drops to 0 of f of x plus h minus f of x all over h. Now, let's see what that means. Limit as h drops to 0 of x plus h raised to the n minus x to the n all over h. Now, this is where we're going to use the binomial theorem. Okay. Now, what we could do is think about Pascal's triangle. And then once you're down, so this would be the 0th row, the first row, the second row, right? This would be like x plus h squared. This would be x plus h to the 3rd. And what we could just stop right here and say, okay, well then when it's to the n, it's going to be a 1, n, some stuff, n1. We could just use that. We could also say, because we did this last year, we could say, okay, well first off, x plus h raised to the nth power. We write that as a sum. And I'm not going to write it as a sum up there, but let's just remember what this is. As k goes from 0 up to n of n choose k, right? X to the, and we could do this either way. I want x to be the big power, so we're going to go n minus k h to the k, right? And everybody remember what that's like, right? This thing just takes care of these coefficients, and the rest of it just ensures that the x's are descending, right, like that, and the h's are ascending. There's an h to the 0, h, then h squared, finally h to the n minus 1, finally h to the n, like that, right? So that's what I'm going to use here. I'm going to use n choose k. I'm going to use this notation, n choose k, when I write this guy out. Okay? Everybody with me? And when I write that out, I'm not going to worry too much about calculating it right now. Let's see why in a second. So, here we go. Something big. All over h. That minus x to the n is going to be right here. Okay, I hope I gave myself enough room. So we know that it's going to be that, the first thing is going to be x to the n, right? Then that's going to be plus, we don't have to worry about back and forth of the minus, it's just plus. So that's plus n choose 1, right? Because the first one was n choose 0, which happens to be 1. The next coefficient is n choose 1, which happens to be n. Then it's n choose 2, which happens to be n times n minus 1 over 2. But we're probably not going to need to get into all that, because you'll see what happens in just a second. Now, x decreases by a power, so that's n minus 1, and h now picks up a power. Now we go to the next one, plus n2 x to the n minus 2 h to the 2. And I do want more room here, because I'm going to say, okay, that pattern continues, and so on, until finally, I guess when x, let's go x squared, and it's x squared, then it'll be h to the n minus 2. We'll have n choose n minus 2. Plus n choose n minus 1 x to the 1 h to the n minus 1. Finally, n choose n is just 1, so I'm not going to worry about it. X to the 0, which is just 1, so I'm not going to worry about it. Finally, h to the n. Right, and that was the same thing I just wrote out when we did it to the third, right? We had, that would be 3 choose 1 x squared h, then 3 choose 2, which happens to also be 3x h squared, then 3 choose 3, which is 1, and no x's anymore, now we have h cubed. I'm doing the same thing, but now I'm just doing it in general, that this happens. Okay, finally, minus my x to the n. Everybody buy that?
Yeah.
This is perfectly general, or this is like, you know, this could have been any polynomial, or any x raised to some integer n, and this is what it would look like, okay? Now let's see what cancels. Oh, look at that. That x to the n is always going to cancel with that x to the n, no matter what it is. So that's nice, that guy's gone. Now what's my part? Can I just plug in an h?
No,
Yeah, I gotta, but I can factor out an h, okay? And I see there's one h here, there's two h's here, so there's more than one h in every single one of these. That's just how it works out, right? More than one h. That one only has one h. So when I factor everything out, in fact, and I'm just going to do it this way, because you know what you're going to do. You're going to factor out that h, and then you're going to cancel the h. So let's just cancel the h. Without factoring it out and rewriting all of this stuff, right? So I'm going to say 1h cancels with 1h. 1h cancels with 1h. And so on and so on and so forth. 1h cancels with 1h. 1h cancels with minus 3, I guess. 1h cancels one of these, minus 2. 1h cancels these, so we have n minus 1. So if that n had been a 5, you would have had h to the 5th. But now you've canceled that, so he comes down to h to the 4th.
Yes.
Okay, everybody with me on that?
Yeah.
So now I have this thing, and I'll actually go ahead and rewrite that so that it looks nice. The thing we have now is n choose 1 x to the n minus 1 plus n choose 2 x to the n minus 2 h plus all the way up to n choose n minus 2 x to the 2 h to the n minus 3 n choose n minus 1 x h to the n minus 2, finally h to the n minus 1. Now can I plug in a 0 for h? And every single one of these goes to 0, and all I'm left with is n choose 1 x to the n minus 1, and let's just do it. N choose 1 is n over 1 over n minus 1! And so, that 1 we could forget about. N is n times n minus 1 times n minus 2 all the way down to 2 times 1. And this is n minus 1, n minus 2 all the way down to 2 times 1. Those all cancel, and all we're left with is n. And like I said, we didn't really need to use this because we could have just made an argument by Pascal's triangle. Because you can see that all of these other coefficients we don't care about at all. All we care about are those first two coefficients.
Yeah.
Because in the end, there's so many h's up here that it's going to go to 0, and it won't matter at all. The only thing that's left is this. And so, yes, f prime of x is equal to n times x to the n minus 1. And now we have this nifty formula. And this is how I think about it, is that whatever power that is, it drops down, and then you decrease that power by 1. Everybody buy that?
Yeah.
Proved. Proven. Has been proven. Proved. We proved it. Okay? So everybody with me on that?
Yep.
Now your book does it this way, and it also does it another way. And so if you want to check out the other way that the book does it, that's kind of cool. It's unnecessary because we just proved it. But there you go. So, put differently, the way that I've been doing it thus far is the derivative of what? X raised to the nth power is equal to n times x to the n minus 1. Or the power drops down and then you decrease the power by 1. So here's an example. Let f of x, no, let f of t equal t to the 7th. Then f prime of t equals
7t to the 6th.
Yep, that's it. It's that easy. It's that easy. Isn't that great? So, like to bring you back to that one that each of you took at least like a page of work to do. This is what?
4t to the 3rd.
4x to the 3rd. Is that easy? It's that, and you see what I mean now. Like, this is what I mean. We're going to take, now that we know that this is true, we don't need to use the definition anymore. We don't need to plug this into a thing and find its difference and blah, 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 and cancel a bunch of stuff. We just do this now. Do you believe it?
Yeah.
Now that we've proved it, do you believe it?
Yeah.
So, yeah, now we're just going to do this from now on. That's really nice, isn't it? Now get this. We proved this where n is an integer. So, what I'm about to do, we don't have any proof of this, so I can't say for certain. But what do you think? What do you think the derivative here might be?
Pi x.
minus 1.
No,
Pi-
pi times x to the pi minus 1.
To the pi minus 1. That's exactly true. We can't prove this yet, but this does work for all real numbers. And when we go into chapter 7, we'll prove it for all real numbers. Later on in this section, we'll get to it Thursday, we'll be able to prove it for negative numbers, I think. But this right here is true, but you gotta wait till chapter 7 until we have the tools where we could actually prove it. But I'm telling you guys right now, if you believe it, if you have faith that it works, use it. Okay, and it does happen to work. It is true that you give me any real number here, doesn't matter what that real number is, any real number, x to any real number is that real number, right there. The same pattern works for any x raised to a power. It has to be a constant power. We're not talking about some number raised to the x. That'll come later. It's a little bit different. But so notice the difference, right? X is your variable raised to a power. This always works. Everybody with me on that? Okay. Okay. I got a couple more I want to do before we move on to the next thing. I'm telling you to take it on faith that all real numbers work. So what do you think this one's going to be?
Negative 2 times
Negative
x to the negative 1. No.
Negative 3.
Yeah, and that is going to be like a big problem for you guys. Everybody messes this up because you're like, oh, you decrease it. You decrease the power, so it needs to get smaller in magnitude. No, you need a -1 from it, so it goes further to the left on the number line, or however you want to think about it. This is true. Okay, that's that. I got one more, and you're gonna love this. You're gonna love this one. Okay, so that is true. It does work, and actually, I think we'll prove that next time that actually does work. Right now I'm asking you to take it on faith that it works for all real numbers.
Negative pi. Oh. 1/2 times x to the -1.
1/2 times x to the -1/2. And that's because you take your 1/2 and you subtract off 1, right? That's all we're doing here for that power. You take whatever that power was, you subtract off 1. 1/2 minus 1 is -1/2. Okay? Okay? So this is true. Watch this. X to the 1/2 is the same thing as the square root of x, right?
Yeah.
Remember when you did this? Remember you did this on a quiz? Watch this. X 1/2 x to the negative anything is 1 over x to that thing.
Yeah.
And that's the same thing as 2 times root x. Isn't that much easier than how we did it before?
Yeah.
Isn't that nice? Like, remember doing this? You had to go x plus h minus root x all over h.
Yeah.
And and that's a pain, right? But what you could do now is you could say, wait a second, if you gave me this, if you could rewrite your function as a power, as x raised to a power, which you can, you could just do this. Way easier. Make your life so much easier. So this thing, don't just think. So this is one of the traps you might get into here, is saying like, well, I don't know how to do, if you gave me f of x equals 1 over x cubed, we haven't talked about how to do that yet. Can you rewrite that as x raised to a power?
Yeah, x to the -3.
X to the -3. And so f prime of x would be?
-3 x to the -4.
There you go. And if you needed to, you could rewrite that like that. Whatever, right? But that's a perfectly good answer right there. Just like that's a perfectly good answer. Even though, when we first did it with roots and a whole bunch of blah, where we had to do this, multiply by its conjugate and all of that, and then take a limit. Now we could just use this rule and say, boom, just like that. It's that easy. Everybody with me? So, pretty much what we're going to be doing, well, there's a lot of things we're going to be doing, but we're going to develop all of this, and then for quite a while, we're just going to be working with this to get you, just like counting on your fingers, right, when you're first learning addition, this is what we're going to be doing. Like, you're going to be given a ton of things to just take the derivative of. And that's, yeah, there you go. So here's the next limit law, or sorry, derivative law that we need. And it's that if you take the derivative of some function, but that function is multiplied by a constant, then that's the same thing as the constant times the derivative of the function. We could do it this way, so that if you have a function and you take the derivative of it, it's that constant times the derivative. Okay, now here's the proof. And this just comes right from the limit laws. This is pretty cool. So let's, and okay, I haven't been writing this. F has to be a differentiable function.
Yeah.
Like if it's not, you can't take its derivative, right? And so we're assuming that the derivative exists. And we're assuming that c is a constant. And like I said, I'm not going to write c as a constant every time I write c. But we're going to say let c and f be given. So you're given a differentiable function f and you have some constant. So then let's let g of x equals c times that thing. So in other words, what we're really after is we have some number times a function that we care about. So like, let's say somebody gave you g of x equals 4 times x squared. You could say, well, that's the same thing as a constant times a function that I already know the derivative of. Right?
Oh,
Yeah, and so that's why, like at first when you see it this way, you're like, okay, all right, when do you have a constant times a function? The idea is, if, you see, this is the key part right there, is like, I know what that is, and so I could just ignore all that stuff and the way I'm going to say this a lot as we do these is I'm going to say 4 comes along for the ride. That's kind of what this means, right? It's like you want the derivative of all of this. Well, you could just pull out the constant and do all of this. But why is that? Well, let's see. This is what I'm saying here. So we're given some kind of function. And I could see that function as a constant times another function, which is what this is, right? So now what I want to do is find the derivative of this guy. So I'm going to say, okay, g prime of x is equal to the limit as h drops to 0 of g of x plus h minus g of x all over h. Right? Yeah. Any qualms with that? Everybody buy that? Just definition, right? Now I could say, well, what is g of x plus h? Well, I would just plug in an x plus h here, and I would get c times f of x plus h. So I have a constant times some function minus g of x is just c times f of x all over h. Can I factor something out of there? Yes, I can factor out a c. Okay, so I get my limit as h goes to 0. I'm just going to pull my c out right here, and I have my f of x plus h minus f of x. See what's going on here? That's just a constant, no matter what it is. I mean, I can even just go ahead and pull that out of the limit entirely, can't I? Yeah. Right? Like, those are the limit laws. And this is what I mean. Like, it kind of follows from the limit laws that you have the limit of two things. It's the same thing as the limit of the first thing times the limit of the second thing. And so here I could say, well, I could kind of even split this up some more and say that's the same thing as c times all of that stuff. And then by the limit laws, that's just the limit as h goes to 0 of c times the limit as h goes to 0 of f of x plus h minus f of x over h. There's no h in there, and so it's just a constant, and so it's just c times the limit of this stuff, which is by definition the derivative. Yeah. F prime of x. So in other words, if you have a function and you have a constant hanging out front, you could forget about that, take the derivative of the function, and then multiply it by the constant afterwards. That's what this means. Okay? So let's do that with this particular function. Just to show, and I'm going to do this one time and one time only, where we're actually going to plug it in and do it. So everybody buy that I just proved this? Can I fill this in?
Yes.
Okay. Prove. Now, what we got here. So just to be sure, let's say I gave you this and you had no idea that this was the case. This is what you would do. Now I told you take the derivative of this using the limit definition. You go, okay, jerk, I'll do that. And so you go g of x plus h minus g of x all over h. And you go like this. Okay, well, what does that mean? I guess I'm going to plug in, that's 4 times x plus h quantity squared minus, that's just that, 4x squared. Now, if you're savvy, what you could do is factor that out. You could factor the 4 out. If you didn't notice it, it's going to get really ugly. Either way, now you see what I'm saying, right? I could just bring the 4 out. In fact, I do want to do that both ways. Let's say that you noticed right off the bat, ooh, hey, check this out. I could just do this, and my life might be a little bit easier. And so that's what you do. Right? And so then you go, okay, well, that's the same thing as the limit. And then you do this 4 times, I guess that's x squared plus 2xh plus h squared minus x squared in there. Right? Yeah. And then you go, oh, ooh, cancels. Nice. And so then you say limit 4 times 2xh plus h squared all over h. And you say, oh, I could cancel. Okay, so I could go limit, I'm not writing the other stuff, or h, pull one h out, and you get 2x plus h all over h. Did I do that right? Mm-hmm. Yeah, 2x h, yes, okay. Those cancel, and now we got the limit as 4 2x plus h, and then you say, oh, I can plug in my 0 for h, and so you get 4 times 2x plus 0, which is 4 times 2x, which is 8x. Yeah? Yeah. Now you may not have, and I'm not going to go back through and write the exact same thing, only where I pull the 4 all the way out of the limit. I could have done it right here where I factored the 4 back in, and we'd have 4x squared, 8xh, 4h squared, 4, then that 4x squared would subtract off with that 4x squared, and we'd have 8x in, blah, 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 blah. You'd still end up at the same place. Yeah. But now that and so now, you see, this is what I'm saying here. Or you could just say, ooh, there's a constant. So I'm going to hold that constant out front and now take the derivative of this stuff, right? And say the 4 just comes along for the ride, the 2 drops down, then the 2 goes down to 1, right? You decrease the power by 1. In other words, this jumps down, you decrease the power by 1, and you get 8x.
A bit easier.
A little bit easier. It's a lot of bit easier than doing it this way. So that's nice. Now we know how to deal with functions times constants. So one more thing we want to do, and that'll make our lives much, much, much easier. Does everybody get how this makes your life easier?
Yeah.
So here's an example. Still working on this right here. How do we want to do this? Let's say that, is that the one I wanted? What did I do? Oh, that was the one I was going to do, but we did that one instead. Okay, cool. Let's do this. Now, instead of writing it as f of x and then say find f prime, I'm just going to say take the derivative of negative 4x to the third. What's that going to be?
Negative 4
Negative
times 3x squared.
Times, because the 3 drops down, right? And then we decrease that power by 1. And so that gives you what?
Negative 12x squared.
There you go. Now you could plug that in to a difference quotient, and it would come out to be the same thing. All right, everybody with me?
Yeah.
Let's see if the camera's died. It has not died. That's nice. Okay, so now here are the next ones, and I'm going to write this out for plus or minus. I'm only going to prove plus, but then we'll do an example that should convince you of minus. So, what? Here. So, take the derivative of what? Well, you can only take the derivative of a function. But let's say that this function is actually the sum of two functions. Or the difference. Or the difference. Or the difference. And your book doesn't have it like this. It goes and proves them separately. We don't need to do that. So what this is, what this turns out to be is you take the derivative of the first one and you add it to or subtract it from the derivative of the next one. Or in prime notation, you could say, if you have a function and it's actually can be written as the sum of two functions or the difference of two functions, then that's the same thing as you just take the derivative of the first and then you add it or subtract it from the derivative of the second.
It's nice.
It's nice. Now, we're going to do the plus case. And like I said, we're not going to prove the minus case, but the example we do will be, you'll see how easily we could prove it if we cared. Here's your proof. Let's say we have a function. We're given some function, capital F of x. And we notice, hey, that function is actually the sum of two functions. So like for instance, let's say we had an f of x, and it was, I don't know, which one do I want to do? Which one do I want to do? I want to have it up here as an example. No, I'll just write something else. Let's say 3x squared plus, how about 2x? Something like that. Now we have two functions. One function, but we could think of it as a sum of two functions. Well, what could we do? we could say, okay, it should just be the case that I just take the derivative of that one and add it to the derivative of that one, but let's make sure that that's true. So f prime of x, by definition, is the limit as h drops to 0 of big F, x plus h, minus big F, x over h. That's the same thing as, well, f, big F of x plus h would be f of x plus h plus g of x plus h. Right? Yeah. Right. And we could think about that as in parentheses or whatever. Minus big F of x, well, that's right there, so I'm going to use some parentheses here, because we have a minus. Okay, so let's rearrange this. This is the same thing as this minus this one. I'm not changing any of this stuff here. Now, plus g of x plus h minus g of x. Yeah? Yeah. But wait a second. I could split this because there's a common denominator over the whole thing. So as a matter of fact, I could rewrite it like this. Yeah? Right? Okay. And the limit of and now we're assuming that, but again, I didn't say this, but assuming that these are differentiable, that is, that these limits do indeed exist. That was the only caveat we had in our limit laws, that if the limit exists, then it's the same thing as the limit of a sum is the sum of the limits, right? Like that. And that's why each one of these things that you'll see in your book starts off by saying, if the derivatives exist. So in other words, if these limits exist, then this step is justified. If they don't exist, well, then you wouldn't have been doing this in the first place. So yes, it all works. The limit of a sum is the sum of the limits, and those two limits are f prime of x plus g prime of x, and that is what we wanted to show, right? Now the only reason I didn't just throw a plus or minus in here is because now when you do the minus of the plus or minus, it's minus plus, and that's just it's just a real pain. But we're going to do an example here in a second that it's a different way of doing it, but you'll see exactly what I'm talking about. Now, in your homework 6, number 19, you had to find the derivative of f of t, and yes, if it's t, you just change all the x's to t's, okay? Your f of t was 5t minus 9t squared. Now, if I didn't have the plus or minus, you might go, oh, you can't, we don't know what to do! Or you could just say, well, isn't that the same thing as 5t plus a negative 9t squared? Yeah, yep, it's exactly the same. And so this is what I mean. Like, we don't need to go through all of this to actually do this. We say, okay, now we have a sum, okay, sum of these things. So, what's its derivative? F prime of t should be, what's the derivative of that? 5, just plain old 5, plus
8, negative 9.
Negative 9 times the 2 jumps down and gets decreased by power, or by 1. So it's just t. And so that's what?
Negative 5 minus 18t.
5 plus a negative 18t, or 5 minus 18t. And so now you see why I just threw the minus in there. Like, you could have just done that at the very beginning with everything. And then but we're kind of using the fact that constants do this, right?
Yeah.
Like, yeah. And so, but you could see why that's the case. I could have just, in the proof, said when you have, let's say our f of x was f of x minus g of x, I could say that's the same thing as f of x plus negative 1 times g of x, etc., right? And so, there you go. And this is what you found, and it took you about a half a page to do that. Actually, I think it took closer to a full page for both of you guys. This was ugly. It's really ugly. Not anymore, right? So this is the great thing about this, is you could just say, okay, if something's broken, if you have a big function and it's broken up by addition and subtraction, you could just focus on each of the individual things. And so, here we go. For this one, you tell me, what is f prime of x?
6x.
6x.
Yep.
Plus 2.
Way easier, right? And so, and why is that? Because the 2 jumped down and we decreased the power by 1, bring it down to 1. Here, you could think about that as the 1 jumped down and then we decreased the power by 1, right?
Yeah,
X to the 0 is just 1, whatever, okay? So everybody got that? Okay. Now this result here generalizes, and this is what's really nice about this, because now we could, nothing can stop us really, because let's say that we had some crazy function that was actually the sum of a bunch of functions, and let's just start with 3. Well, we could say, okay, the derivative of that is the derivative of this, and this tells us that this should be the same as taking the derivative of that and the derivative of that, right? We can just pretend that that's one function, whatever that is, and say, just take the derivative of that thing. Well, that thing happens to be the sum of 2 functions. And so, that is just f prime of x plus g prime of x plus h prime of x. And so, and we could do an induction proof, but I don't think it's necessary. You see what's happening here, right? Any sum or difference, you could always just break apart and just do individually by each of its terms. Yeah?
Yeah.
Okay, so here's another brutal one that you had in homework 6. This is homework 6 number 21. You had f of x was equal to x cubed minus 3x plus 5. This one was terrible, but now watch this. I just need one line. What's that?
3x squared
3x squared.
minus 3
plus 0.
5 plus 0. 0.
Oh! And that's what you got. That was the answer. So polynomials are now the easiest thing to possibly take derivatives of. Let's make one up here. Oh, I'll multiply that times 17. How about 10? Minus 9. What's something easy? There we go. Now, how about plus 10x minus 457,000? Okay. Now, prime of x is equal to
27x.
Wait,
what?
30x. Wait, 30x to the 9.
Why 30?
27, right?
Why 27?
Because 3
Why,
times
it's
9.
10.
What is your 9? The 10 drops
30.
down. 10 drops down.
30x to the 9.
3 times 10 is 30. Yeah, I know. And then, so, okay. Let's finish this up and then I got a spiel, okay? And then, now, just minus, you just copy the thing. Now, what do you get here?
18x.
18x to the what power?
0. 1.
1.
Okay.
Plus 10.
10.
Plus 10.
Plus 0.
Yeah, there we go. Okay, real easy. I think you might have
You
a
can
problem.
factor out 2.
I don't care. I doubt it. I mean, something in the 9th power.
Really could.
You can factor out 2.
Oh yeah. I see what you mean. I thought you meant
Why?
like try to factor that. Ugh. But yeah, you could. It doesn't matter. Okay, now here's the thing. So when you first learned multiplication, you learned how to multiply like 2 small numbers. You probably learned your times tables or whatever you called them, right? And then you learned how to multiply bigger numbers together. Then what was the next thing you learned after multiplication?
Division.
Division. You learned how to undo the thing that you learned how to do. Right now, We're learning how to go from here, given a function, find its derivative. Can you guess what we'll be doing later?
Redoing derivative to function.
Going from derivative back to function. That's called taking an antiderivative. Okay, so you have going in this direction is the derivative. Now you could imagine I have some function. And it was originally another function, and I took its derivative, and now this is what I got. Where did you come back? And so we're going to be going back to that. And the reason I bring this up is because you said, well, you said 27, right? Because of the thing. And this, your brain will be so messed up when you start doing this because you always ask, which direction am I going? Am I making the power bigger or smaller? And so it's kind of a pain, right? It's just one of those things that you're going to have to, every single time, you should do. And so what I suggest that you do now, as you're learning this, is every single time you see a power, say in your head, power drops down. And so power drops down, and that's how you get that. The power drops down, 2 times 9 is 18. Power drops, right? So this is to keep you from... To make things a little less crazy when we start doing these backwards, when we start going in the reverse direction.
If you took an antiderivative of the one we just did, how would you ever know that there was the 35,000?
You never would.
Is it just
It's kind of like if I said, I know I've been driving at 60 miles per hour for 2 hours. How far, you could tell you how far you went, but you wouldn't be able to know where you started.
Oh, it is.
There's though there's reason to my rhyme.
That's the Y.
That's the Y. That's the Y-intercept. Interesting. So I think we have a little bit of time. I do want to go over that little spiel that I was going to say earlier. So we had this limit. Limit as h went to 0 of 0 over h. Now real quick, let's just note that that's the same thing as the limit as x goes to 0 of 0 over x. Why would I call it x? Well, because what I'm about to do, we think about this in terms of x. You could think, anytime you have a limit, you could, a ratio in a limit, you could think about this as being a limit. And this could be going to any number. This could be a. When I'm about to draw, we'll make it just be easier on me if I make it 0. It doesn't have to be 0. But we could always think about this as the limit of 2 functions. Or, I'm sorry, as the limit of a ratio of 2 functions. Where you have some function, f of x, over some other function, call it g of x. Okay? And if the g is going to 0, okay, so we're supposing that g goes to 0 as x goes to whatever it happens to be. It could be a, but just to make my life easier, I'm going to say 0. For this limit to exist, what must f go to?
0 as well.
It also has to, because if it goes to any number that's not 0, well then your limit does not exist, right? Right, if it goes to 5, as this gets closer to 0, it's going to blow up, right? If it goes to -7 and that gets closer to 0, it's just going to blow up too. So the only way for this limit to exist is if they're both going to 0, given that we know the bottom's going to 0. And that's what we're into right here. The bottom's going to 0. Same thing as this, the bottom's going to 0. So let's think about let's think about a function that does that. Or 2 functions that do that. My claim is that that function goes to 0 as x goes to 0.
Yeah.
I think that's correct. And I claim that this function goes to 0 as x goes to 0. Is that the case? Okay, let's see what's going on here. Well, one thing we could do is you could just say, well, the limit of f over g, I do want to keep this color coded here. So I'm going to do this. We could say the limit f over g is the same thing as x squared over x, which is just what?
X.
That's just x. And what's the limit as x goes to 0 of x?
1. X.
No, it's 1.
No.
Oh, wait.
Hold up.
Oh,
Hold up.
zero.
The limit as
I was thinking
x.
derivative, yeah.
Good, right? I know. All right. And so the limit is just a big fat 0. And so let's see what's going on here. Two functions on the same graph. We have f, which is x squared. He looks something like this. And we have g, which is something like this. And we're talking about what happens as x gets closer to 0, right? So x is here, and we're going this way. Well, in both cases, g is approaching 0. So is f, but f is getting there much quicker, isn't he?
Yeah.
F, and we could say f is going to 0 faster than g is going to 0. And so f dominates this. He's going to 0 much faster, and so he gets to 0 first. That's why this happens. You could think about it that. That's one way of thinking about it, and we'll formalize this later on. However, that's not the end of the story, because just because we have two functions both going to 0 doesn't mean that it's going to go to 0. Watch what I mean. Let's say instead of x squared, we had square root of x. Now, what does that reduce to? Root x over x.
Multiply the 1 over x.
1 over what?
Oh, root x.
Oh, come on, guys. I know, right? Because x is the same thing as root x times root x. And so you put that over root x. You could cancel one of them out and you're left with that. Now, what's the limit of that as x goes to 0?
Also 0. Not 1, wait, 0.
1 second. Okay, so look at this. What happens? Can I plug in a 0?
No. It's infinite. Well, but it doesn't exist.
It doesn't exist. We could say plus or minus. Who cares? The point is, it doesn't exist. Why is that? Well, on one hand, we have g, which is just plain x. It looks like this. And we had f, which is now root x, and so he does something like this. And we could see, okay, they're both going to 0, but who gets there faster?
X.
We don't. Yeah. Oh, I meant which function, the name of the function. You're right, because I forgot what we were talking about. G gets there faster, right? Because when they're here, G is still up here. When they're here, G is still up here. When they're here, G is still up here. And so G's getting to 0 faster, so he takes over and blows up. And so you might think, okay, well, if one function's on top of another, then that's what depends, right? You want your one on the bottom to be blah, 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 blah. It's a bit more complicated than that. Watch this. So in that case, it blew up because f was bigger, we think. Well, here's an f that's bigger, right? That's bigger. In fact, he's always bigger. Like this.
Oh, I think we should.
Right?
Yeah.
F is bigger.
G still gets there first.
But watch what happens. G still gets there first, but now we have the limit of f over g. That's the same thing as the limit of 10x over x. What does that reduce to?
10.
That's just the limit of 10, which is just 10. And so he doesn't blow up. Ah, that's weird. We will figure out why this is... We're going to get into this later on. It's not simply that he's bigger. It's the rate at which they're going. They're both going at the rate of one is always 10 more than the other. He's always 10 more. He's always a factor of 10 bigger. When we had this guy, now the rate is steeper. This guy's going down much quicker than this guy is going down. It's not always a constant amount. That's why he kind of wins out. It's the rate at which. It has something to do with the rate, which is what we've been talking about. The rate of a function, it has to do with its derivative. But here's the big, this is the big takeaway to get to the bottom of this. Now, let's think about the difference. So we saw a second ago when this guy was the case, when f of x was x squared, and g of x was just x, then f dominated and the limit was 0. Why? Because f was getting to 0 much faster than g was getting to 0, right? Everybody with me on that, right? So the limit of f over g is the same thing as the limit x squared over x, which is the limit of x, which does indeed go to 0 as x goes to 0. But we saw graphically that f is getting there much, much, much quicker. Now, finally, to bring this all home, I want to convince you, who's getting there quicker? That guy or this guy? If f is 0, he's already at 0, right?
Yeah.
And so, like, who wins out? Well, the guy who's already there. He's already there. He's not trying to catch up or whatever. This guy isn't trying to catch up to this guy. This guy won the race already, right? And that's why this thing right here is 0. Everybody buy that? Does that make kind of more of intuitive sense, right? There's that weird stuff I was saying about it's not always who's taller or whatever. That comes later. We'll get into that. There's a really cool rule that's very, very, very useful for the rest of your mathematical career. But this is just this idea I want to present to you is, does a limit blow up just because this is going to 0? Well, not always. What's a way we could think about it? Well, we could think about it as two functions heading to 0. And it's whoever's getting there faster. And if the function itself is just the constant function 0, he's already there. And so he dominates always. So that's why that limit is indeed 0, and why the derivative of a constant is, yes, 0. That's all I got.